Okay. Hello, everybody. Let's try to get started on time. Welcome to our first parallel session on interpretability. So this is the GERN stage. If you are not in the correct session, you can, I guess, still move on to the lab stage. But we have quite nice and exciting talks on interpretability, and this is also immediately followed by the poster spotlight presentations, so stick around until that as well. Q&A time will be 2 minutes per talk, so you can raise your hand to ask questions, but you can also ask further questions at the speaker corner over here after the session ends. And yeah, with this, I am very happy to introduce our invited speaker for this session, Vreeken. Yils is a tenured faculty at the CISPA Helmholtz Center for Information Security, honorary professor at Saarland University, and fellow of Alice. His research focuses on developing well-founded theory and efficient methods that give clear and actionable insight into complex data and models. More generally, he likes data mining, machine learning, and causal inference, and is especially enthusiastic about applications in health and science. Welcome, Yils. We are looking forward to your talk.
Thank you, Hannah, for the kind introduction and actually for the invitation. I mean, it's always great to be on stage and tell about, well, the work that I've been very enthusiastic about and have been working on with all my PhD students, some of whom are in the room right now. Learning actionable insights from data models. That's what today's talk is about, and specifically from scientific data. Let's go over a few possible fields or a few possible points of interest that you may have here in the room. I mean, there might be some physicists in the room. Suppose that you are interested in developing materials that are particularly conductive or have other particular nice properties or bad properties, depending what you want to optimize. So you have a bunch of either simulated or real materials, could be gold nanoclusters, this is a particular example, and you would like to find out which subpopulations behave now particularly specially. Another question you might have is that, well, I don't really care about learning how these molecules work. I already have a model that predicts super well. I love my model. However, when can I trust it? Under which conditions? What are the domains of applicability of my model? Can we find out under which conditions, for which particular inputs, you can trust your model? It's almost the same question, interestingly enough. And then one of the topics that I'm particularly interested in lately, suppose that we're considering a particular type of treatment. It could be a novel treatment. We might have some interventional data, and it might have a lot of observational data. I mean, so we can give these, well, let's say we have some novel drug, and we can set up a drug trial. Well, this drug, after the fact, we can determine, did it do something, yes or no, under the conditions that we tested. But for some populations, this drug may be particularly effective. And for others, it may not do anything, and for yet others, it may actually kill more patients than it saves. Can we somehow find out who are those populations? Those are the 3 topics, or actually it's just one topic, but those are the 3 topics that I want to discuss with you today. So I'm going to start with, can we find subpopulations in data? Then we're going to look into, can we find subpopulations for which your model, your arbitrary machine learning model that does prediction, does well. And last but not least, we're going to look into time to event or survival data. Let's start with the first part. As a simple example away from physics, let's start with census data. I mean, because there, all of us, regardless of whether we're a physicist or a medical expert or whatever your background is, we have some intuition. We have some census data here where we have for a small part of the population here, we have the biological sex, we have their height, we have their ethnicity, we might have their weight, we have their education, and so on and so forth. And in this particular example, we're interested in figuring out, are there any subpopulations that make a remarkable high amount of wage, have a high income, or remarkably low, or somehow stand out. One population, or one method how you could go about this, is actually just doing this by hand. We could say, you know what, we have some intuition, we're going to split the data by height. We somehow have a gut feeling that people below 180 make more or less. Let's test this. We can do this as a hypothesis. We can approach this statistically. We can say, okay, well, maybe biological sex has something to do with it. But in the end, if we do this by hand, we're limited by our own imagination. And, of course, the amount of time that we have, because there's an exponential number of combinations of these conditions that we can test for, and nobody has time to do this. For this, there is a subfield in data mining, which is sort of like the other side of machine learning, focusing on getting insights that matter for humans, called subgroup discovery. I guess that very few people in this room have ever heard of subgroup discovery, but I do hope that some of you know what a subgroup is, because that's technically just a subpopulation that we can give a name. Let's say, in this particular data, if we run this approach, it could be that women with a particular low education, let's say they never went to high school even, well, they make a remarkable low income. Not a surprise, of course, right, to anybody who knows how demographics and everything works. But this is a type of a result we could get from census data. On the right-hand side, we have also a few other results. So men with particular high education that are above 30 have a very different distribution than the overall population. This is a hypothesis generator. Now, for census data, is this particularly actionable? Is this particularly interesting? No, but I just wanted to give you the intuition. So subgroup discovery, how does this work? Traditionally, it needs basically 3 main ingredients, and each of those are problematic. First of all, it needs to pre-discretize any continuous valued attributes. That means, in the previous example, age groups. We would need to somehow group people into low age, medium age, high age, or however fine-grained you want it. And then you need to search over that. That makes it combinatorial. That is going to be very, very slow. So if you have many features with many possible ways how to discretize, you're up shit creek and you're in definite need of a paddle. Also, what is a big problem is that we need very strong assumptions about how the world works. What type of exceptionality are we interested in? Should the mean of the subpopulation be different? Should the mean and the variance be different? Should there be other properties that are different? For each of those different types of ideas, these different types of exceptionality, different methods have to be developed. And that held back subgroup discovery as a field from being applied. Along came, well, not a spider, but particularly Jannes, Niels, and Sasha. Niels is sitting over there. They did not like this picture. They liked the idea of subgroup discovery, but they did not like that all these particular nitty-gritty ingredients are holding it back. And they came up with some great ideas, stealing ideas from continuous optimization, basically deep neural networks. They said, you know what, we're going to learn discretizations on the fly. We can use a smart architecture to figure out what are the optimal or near optimal intervals. We don't like to make assumptions about what is exceptionality. Let's make this as general as possible. Let's consider divergence of distributions, and particularly KL divergence. In addition, because in the end, in order to determine the KL divergence, we need to learn a distribution. Again, assumptions. They don't like it. We can use normalizing flows. We can learn these end-to-end, and we get a non-parametric estimate of the distribution. So in the end, you do not need to put in the assumptions about how the world works. You can let the data speak for itself. And then, this was the actual brilliance, because the first 3 are nice desiderata. They managed to make a continuous, optimizable, end-to-end framework. I'm going to go through 2 of the magic ingredients that were particularly, I would say, impressive that they managed to do. Because these subgroup descriptions are effectively conjunctions of predicates, basically conjunctions of conditions. Now, suppose that we have in our data whether somebody smokes or not. That is relatively straightforward. I mean, either an attribute is that has to be 1 or 0 to be sampled in or out. But what about these intervals? How can we learn those? Well, we would need a differentiable binning predicate. And that is problematic, because intervals are very strict. Either you're in or you're out. How can we smooth things? This is what a standard interval looks like, right? A very boxy function, right? And as you can see at the corners, it is not very differentiable. So how can we fix this? Well, let's close our eyes and let's think of the most easily differentiable or most smooth function. I guess, well, I see many open eyes, so you're not listening very, very attentively, but if your imagination is working, probably you're thinking of something that looks like a Gaussian. Gaussians are nice and smooth, but Gaussians, at the same time, they don't really have this interval type of interpretation. Where does the interval start? Where does it end? Huh? Now, rather than actually instantiating this as a Gaussian, which normally you have a mean and a variance, what we actually did over here, it looks a bit intimidating, but effectively it's 2 exponentials sort of glued together. And for an exponential distribution, we can adjust the slope. Now, and that is the key idea that the guys exploited, because that slope, we now translate it into a temperature. At the beginning of the optimization, the temperature is high. We have a very nice and smooth distribution. But then during the optimization, the temperature lowers, lowers, lowers. The exponentials become sharper, sharper, sharper. And in the end, in the limit, they have, well, exactly an interpretation of an interval. And we can even prove that this is indeed has a logical interpretation. So we can use continuous optimization to get a very nice, crisp definition of an interval. This is cool. Okay, well, that means that we can solve intervals, but it doesn't mean that we're done. Because smoker and being in a particular interval. An AND operator is also not particularly optimizable. This is also a yes or no, so we would again be stuck in combinatorial optimization. So there, another idea came in, namely, why don't we just use a harmonic mean? As simple as that, I mean, of course, getting to the idea took a little bit longer, but simply taking a harmonic mean solves the problem in its entirety, which means that we now can from, let me see, whoa, okay, this is very, okay, we can get the predicates that I just saw. I'm not going to use the pointer, that's too scary. Up, go away. We can combine them in such a way that now for the points that are selected in, automatically the distribution is learned. We have in the background the distribution we've learned over the entire population, and now we can maximize the KL divergence between these two distributions. Basically, filtering or pushing back the information to the predicates and how they are combined. And for that we have, oops, there are you, we had weights per predicate. So we have an implicit feature selection. In the end, after a bit of learning, I can identify exactly which features are relevant and in which intervals they're relevant and which combinations they're relevant. So everything is fully differentiable. Okay, this I'm going to skip, because this is not so interesting right now. Let's move immediately to some applications. Can we use this, right? Because if you want to read more details, we can read the paper. Let's start with an example from material science. Gold nanoclusters. Gold nanoclusters are interesting because they're used in photovoltaic panels. In photovoltaic panels, you want to have as much yield as possible, right? I mean, you want to catch as many of these photons and turn them into energy as possible. At least this is what material scientists are super interested in. We have, for each of these gold nanoclusters you could put into a photovoltaic panel, we have a number of atomistic features. For example, atom-based features, how many atoms of what kind do we have? Bond-based features, how are they connected? And what shape does this molecule then take? What we're interested in this particular application is the so-called HOMO-LUMO gap. That is the difference between the highest occupied molecular order and the lowest unoccupied molecular order. Effectively, how big a distance can the electron move within this molecule? How much energy can it absorb? Right? That's how you can think about it. Now, back in the 90s, people were thinking hard about this problem, and they found out, pretty much painstakingly, that atoms or molecules with an odd number of atoms and molecules with an even number of atoms behave very differently. There's a very big gap between those. If we now look at the results that our method finds on data of this kind, and okay, I'm still going to try it again. Let's see, where are you? Oh yeah, ooh. Okay, I'm not going to try this. Does this work? No, not going to do this. I'm just going to do it like this. Key. I'm not doing anything right now. Odd number of atoms, even number of atoms, right? I mean, not. And particularly, this is then interesting, there's things on the right-hand side. The left-hand side could have gotten us a Nobel Prize back in the 90s, but that was already stolen from us. However, the number of bonds and the shape of these molecules, that was completely novel information. That led to a award-winning publication in the New Journal of Physics, even though our method doesn't know any physics, and I don't know any more physics than I learned in high school. So was this interpretable? Yes, right? So in that sense, I think this part of the talk belongs in this session. Is this actionable? Well, yes, because now the material scientists know which types of molecules to put in the photovoltaic panel and which not. Can we do this only for one-dimensional targets, like a HOMO-LUMO gap? No. Matthias Wilms, together with Sascha Schur, for his master thesis, extended this framework to multivariate targets. So right now, here we have, well, let's just imagine it's the same target, but then all of a sudden we have now split it into 2 dimensions. We can figure out names for each of these clusters without even having to give the number of clusters, without having to give it any physics ahead of time. Each of those, the colors correspond to one of those rows over there, and the blue bars are the conditions, just the way how we came up with visualizing this. So we can characterize how subpopulations work without knowing any physics. This is pretty neat. Let's move to the second topic, because maybe you don't care about physics, right? Maybe you don't care about getting these subpopulations for your tabular data. Maybe you just have your machine learning model already. I stick within the realm of material science because there I have a neat example. Here people were, again, interested in predicting the efficacy of particular configurations of photovoltaic panels. There were a number of challenges, and a number of really potent models were developed. Well, how do you develop a model? You minimize the error. And if the error is too high, well, you poke at the model until the error goes down. That's just the arbitrary setup, right? That's you have some target, you want to minimize something, whatever you want. You will, in the end, get an average error, the one that you want to minimize. Our collaborators were very happy to get an error of 0.0481, because this was below chemical precision, meaning that if they go in the lab and would repeat it, they would get a higher variance than what this error already gives. So basically this model is like, oh my God, this was fantastic. Then we asked Mario Bolai in the top right corner, have you looked at the distribution of the errors? And our collaborators were like, okay, well, no, we don't really want to because we like this number. Like, well, let's look at it. And then we got this plume. And that made our collaborators very sad. Because as you can see, the average error is indeed very low, but there's many, many instances with very high errors, much higher than this chemical precision. This means that this model, for some instances, you can trust it. For other models, or for other instances, it does arbitrary things, right? You can basically well just flip a coin. Now, then we thought, rather than trying to predict directly, let's say, a homo-lumo gap, we can also now make the target of our subgroup discovery the difference between the predicted value and the target value, basically the residual. Can we find subpopulations with a particularly small residual? And the answer is yes. I'm not going to go through all the details of this particular model, but the explanations made complete physical sense. Effectively, the more compact the area that the model is trying to describe, the better it predicts. Even better than that, for those instances that fall within these very general descriptions, the error is even lower and below chemical precision. So effectively, we can really say, apply here, don't apply there. Thank you. Good. So now to the final part, survival analysis. Survival analysis, the idea is that we have, let's say, some treatment 0, treatment 1, we have a number of patients, and the clock starts to tick at the time of diagnosis. If the data would be complete, we would be pretty good, because we can sort of treat it as a prediction task, right? And if for a certain group the average is higher, then okay. We can turn it into a survival curve. We can then see, okay, what is the difference between the two populations, and all is fine and dandy. However, humans have this nasty trait of sometimes surviving beyond the time, so we don't know if the time of event, which often is death, whether it occurred or not. Sometimes they leave the study because they're sick and tired of being prodded at. So our data looks a bit like a mess, and we can't use standard regression. Can we find subpopulations of people that respond particularly well or particularly badly to treatment? Is this a subgroup discovery task? Yes and no. The good parts of SyFlow we're going to take. And in addition, we're going to drop the parts that do not fit this problem. Namely, we're going to replace normalizing flows with random survival forests, KL divergence with the difference between the two curves in the top right corner, and we use exactly the same machinery. That allows us not just to perform much better than the state-of-the-art on synthetic data, get a lot of bold numbers in a table, which hopefully helps to publish the paper, but this is the last result, and then I'm done. This is the population. This is the survival curve of the population. These are two subgroups that we found that respond particularly well to the treatment. Basically, if these patients pop up, give them the treatment. That is cool. These, don't treat them. These patients, and this was exactly the task here, this is a collaboration with DKFZ, if we treat them, they're going to die more quickly and more painfully than if we would not have treated them. Is this actionable? Yes, because we can also give insight in why this is the case. So the doctors don't just have to trust what we're saying, they can also understand what is going on. Now, I don't have time, sadly, to introduce the brand new results together with Omid Jervani, but we're looking also at the prediction of stroke treatment outcome. And we find subpopulations that respond particularly badly to treatment and particularly well to treatment. Okay, that brings me to the end. I'm going to click through this. For each of these methods, implementations are available. I'm super happy to take questions as well as to discuss afterwards in the Speaker's Corner. Thank you very much for your attention.
Thank you, Gilles. Yeah, we see Fabian has a question.
I'll moderate the session.
Thanks for moderating. Cool stuff, Gilles. I think it's important to find, for example, like survivor subgroups and so. In this particular example, it looked nearly bimodal, right? So there was sort of the overall average curve, and then you had a few in the bottom, few on the top. Did you leave out a few additional groups that were sort of filling up the rest, or was it really that drastic? And in particular, was this on replication data, maybe even independent cohort or something?
Oh, replication data, no, not yet. In that there's an ongoing trial. In that,
but it was a holdout, right?
But otherwise, yes, sure. And second, I mean, the bimodality, I mean, here these were the strongest subgroups we find, because we're trying to maximize these differences. But there's plenty of populations in between as well. That, yes.
Okay, perfect. I think we have a quick question from either Carsten or Zeynep.
Thanks so much for a very exciting talk. I have several questions actually, but maybe...
We have time.
Okay, that's good. So the first one is about scalability of that method to sizes of input data in terms of the number of variables.
Yes.
So like how does this deal with a large number of variables?
Define large. What is large
like,
for you?
For example, if I have gene expression data, this comes for thousands of genes.
Exactly. So the current instantiation, the ones that you've seen, they work with thousands. They start to, depending on how much data you have, because in the end, I mean, statistical power is also a thing that bites us in the back, even with continuous optimization. So if you were to have tens of thousands of variables, we need also quite a bit of data. Pushing it beyond, let's say hundreds of thousands of variables, we have other methods that, well, are slightly more specialized, but we try to serve the entire range of things.
Okay, great.
Yep.
And I also have a question.
Maybe,
okay,
if it would be okay, I would
I can
move
that to the speaker's corner.
Terrific.
Thank you.
Looking forward. Thank you very much.
Thank you so much again for your talk. And now I would like to welcome Samuele